give you one little important application of Faraday's law here, and it's the case I could dream up here of having a magnetic field that points into the screen and a square loop of wire, and I'm kind of trying to draw this from two different points of view. On the right-hand side, you're looking at it from top down, and on the left side, you're kind of looking at it end on, so as if you're standing off to the left side of the screen looking at this thing edgewise. So what happens if I take this thing and flip it within this 1 Tesla field, it's a 1 centimeter square loop, and I take it and flip it over, so now it's pointing the other direction, there will be a change in the flux to that thing. So if I keep this thing spinning at 60 hertz, I'm going to have a flux that's developed, a flux change that's going to develop an EMF according to Faraday's law. And since the case here is that the field in the area are constants, I mean, it's not like the wire is changing shape and it's not like the field is changing magnitude. It's just the angle between them that's changing. So the flux, BA cosine theta, it's that cosine theta term that is what's getting this done for me. So let's take a look at this. This thing's flipping over and over again. That means that the theta actually is a function of time. I've kind of drawn a stop action partway through the process here where theta is tilted over, and you can see that there's an angle between the A vector, the area vector for that loop, and the field B. And what I'm going to say is theta actually depends on time. It's equal to omega t, where omega is 2 pi f, and the f in this case is 60 hertz. It's 377 radians per second. So what I can do is plug in some numbers on this thing. I get that taking a derivative on that cosine theta, I get omega sine theta, sine omega t. So the EMF developed is B times A times omega times the sine of omega t, or that works out to be 3.77 volts times the sine of 377 t. So what I've got here is an EMF, a voltage that comes out of this loop, if you will, and the current gets driven by it, that is peak to peak, goes to positive 3.77 volts and then dips down to negative 3.77 and back and forth at 60 cycles per second. What I've got here is a generator of alternating current. And this is pretty doggone important because I could hook this thing up to, say, for instance, a handle or a turbine or a windmill or something like that sits there and spins this thing in this magnetic field all day long. And I've got an electric generator. It's an AC generator that will then take this this motion of the wind or whatever it is that's making it turn and turn it into an alternating current of electricity that I can then use for some other purposes down the road. Now, this is our first step into talking about alternating current, and things are going to be a little different in some cases than we had with direct current. And that's what we'll deal with in the next chapter primarily, but I wanted to introduce to you why it's important to us, because it's pretty easy to generate using Faraday's law. It also should be no big surprise that I could probably do the reverse of this. If I had some way of running an alternating current into that loop, I could get it to flip over and over again. So a generator, in one sense, where I'm pulling the current out, can also sort of be run as a motor. So if I have a way of alternating the current into the loop, I can make the loop flip around and around. It's a little trickier because you've got to get it going somehow, and there's some issues to deal with in terms of how you make contacts and so on. But nonetheless, it's a very fundamental thing in terms of our use of electricity.